off with Newton's first and second laws. This all begins though with understanding of classical mechanics. So what we are talking about really has a range of application. Classical mechanics describes the relationship between motion of objects in our everyday world and the forces that act on them. But this is only true when we are talking about our regular sized objects that we see. So it doesn't work for very tiny objects. It doesn't work for anything that's moving too quickly, that is close to the speed of light. And we'll get into quantum mechanics for that, not to be talked about right now. But in our classical mechanics, of course, we have definition of force, and Newton's laws are based on our understanding of force, which on a basic level is a push or a pull. Of course, we can have contact forces like you see in the pictures on the left, or we can have field forces that exist between objects, and typically we're talking about these fundamental forces of matter. That is, just for review from chemistry, there's 4 fundamental forces that govern the interaction of matter. That's a strong force, the weak force, electromagnetic force, and gravitational force. And in the order they are here, goes by strength. It also shows us, well, strong force, though it's incredibly strong, works across an incredibly small distance. Versus gravity, that's incredibly weak in comparison but works over long distances. But we'll get into those forces more later. Okay, Newton's first law is often called inertia. I believe that you've heard it, so here's a little review. That is, something's moving, it wants to keep moving, and it will keep moving forever and ever and ever unless something interacts with it, some external force acts on it or gets in its way. Or an object at rest, that is probably you sitting on your chair right now, will stay at rest unless something acts on you and causes you to move. So that's mostly review. Let's make sure we're clear on our terminology. An external force can be anything from outside of the environment, and we define the system. So from outside the system that we're talking about, in the case I gave you, the system was you sitting on your stool. So an outside force would be your little brother or sister coming and pushing you. That was outside of your system. A different way of talking about Newton's first law would be, or a different way of stating it, is that if there's no external force, then the acceleration on the object is 0. Which means you could be in motion, but you're going to keep moving at that same speed forever and ever and ever unless there's an external force. Outside force causes you to either speed up or slow down or change direction, but for sure will change your velocity, so there is acceleration acting on you. Here's an extreme inertial state. That is, that train was in motion and there was not enough external force to keep it from its motion. That is, until it went through the window and smashed to the ground. It had a lot of inertia, so their tendency to do this is inertia. The fact that an object wants to keep its motion, the state that it's in, is its inertial state. And so this train had a lot of inertia because inertia is based on mass. While it was moving, it wanted to keep moving, and it wanted to keep moving really, really badly because, of course, it's incredibly massive, so it takes a lot of force to stop it, and this time they did not have enough force in it. To us, mass, of course, is a scalar unit. It is a quantity without direction. It just has an amount, and we measure that in kilograms. The amount of inertia an object has is based on its mass. More massive, more inertia. Less massive, less inertia. Okay, Newton's second law is basically an equation. I like to call this one your ma, only because it is the equation that force equals mass times acceleration. That's ma, not mom, ma. So acceleration of an object, though, is directly affected by, that's a directly proportional to net force. If I put a force on an object, it will accelerate. If I put more force on the object, it will accelerate more. And it's inversely proportional to the mass. So if I put a force on a refrigerator, it will accelerate a little bit. If I put that same force on, say, your stool, it will accelerate more. If I put that same force on something very light, less mass, like a pencil, it will accelerate a lot. So those are inversely proportional to each other. When we put it together, then acceleration is directly proportional to the sum of the forces. That's what that symbol is showing. And inversely proportional to the mass. So mass is on the bottom. Or another way to write this is that the sigma F, that's this symbol again right here, sigma means the sum of F. So sum of all the forces added together is equal to mass times acceleration, which acceleration is a vector quantity just like force. So F and A are both vectors and can be applied in 3 dimensions. In fact, just like we did with projectiles, we'll be breaking force down into its x component and y component. We could even break it into z component, just like we could have done with projectiles. Another way to think about this is that acceleration can be caused by the force, but it is resisted by the amount of mass. Okay. As we break it down so that we can also think about that in terms of its equations. So if the sum of all forces, which again that's what this symbol represents, the sum of F, or the net force, the sum of all the forces added together, is equal to the mass times acceleration. That's the sum of all mass times acceleration. So if we break it down into its components, then we can say, well, the force in the x is equal to the mass times acceleration in the x direction. Force in the y is equal to mass times acceleration in the y direction. Force in the z is equal to mass times acceleration in the z direction, and that will make it easier for us when we're solving later on. Units of force is the Newton, named after Sir Isaac, this series of videos. And 1 Newton is equal to a kilogram times a meter per second squared, which you'll notice that looks just like kilogram, which is mass, and acceleration, which is measured in meters per second squared. So when you multiply those, mass and acceleration, if you have them in the correct units, you will get a Newton. Here's some references for you to our other systems, but of course we will use SI. That's the Newton. So let's try a problem. Here's a bullet leaving a gun. We know the speed is 320 meters per second. What total force, so we're just looking for the net force, we're not even going to break it down into components, just assumed constant force is exerted on the bullet while it is traveling down the barrel. And this took 0.002 seconds, so we're also given the time of that force acting. Our equation is force equals mass times acceleration. This is Newton's second law, your ma. And we know mass. Look at that, 5 grams. That's given to us. What we don't know is acceleration. Oh, but look at that. We know it gets a speed of 320 meters per second and that it took 0.002 seconds, so we can pretty easily solve. And please pause it and solve without me first, but let me show you the answer. 320 meters per second is the change in velocity, right? It went from 0 to 320. Therefore, acceleration 160,000 meters per second squared. We plug that in. Again, solve for your F, and then let's see if you get it right. So F equals ma. Now, in order for mass, or only in order for force to be in newtons, the mass needs to be converted to kilograms. So 5-gram bullet would be 0.005 gram or kilograms bullet. And we multiply those out, you get 800 newtons. It's a lot of force. Or in order to get our right sig figs, which is 2, we need 8.0 times 10 to the second newtons. And that is the end of Newton's first and second laws.